We are also live on YouTube. I'm going to send a link. So if you want to go to YouTube, you can do so. Okay, so this is my first class that most of the students are online. It's a weird experience. It is better than last year, though. You remember last year after March? It was hectic. It was bad. Ah, you were in the co-op, right? Okay. So let's start the class. We have a couple of people online, and Trey and Nicholas in class. So you had the exam, flight mechanics exam. Hopefully the exam went well this time. You had enough time, more than enough time, to answer all of the questions, hopefully. And I haven't graded the exams yet, but I'm hoping everyone will get an A. And at this point, what I'm going to do for his second exam, just to make sure this doesn't happen, is your second exam in general is going to be a little different. It's a little more mathematical. So the concepts, I guess, are harder, if you will. A little, just a little more mathematical, not that much. But we are going to have, instead of having this long questions, I'm going to give you 2 problems and a couple of descriptive questions for 75 minutes. But for your fun, yes. The descriptive problems, like 4 through 6. Yes, 4 through 6, yeah, those ones. And yeah, like I'm going to ask you what are the Kepler laws, which are the. I know. Okay, that's good. Which are essentially the meat of orbital mechanics. At least the stepping stone of orbital mechanics. And yeah, is there any questions from the online audience as well? Are welcome to ask questions. And okay. So we are going to start the orbital mechanics part of the class. Orbital mechanics, the reference book is Orbital Mechanics for Engineering Students. Dr. Curtis has written this book. I have the book right here. We have the 4th edition of the book that just came out last year. As far as I'm concerned, you don't need to purchase the book. I will cover whatever you need in the class. And except for the bonus points. So I may give you a couple of bonuses that you need to go to the book and look it up. Or you can solve it on your own. You actually have a couple of bonus points today as well. And we are going to start with the main part of the, let me actually bring up the table of contents. The main focus of our class is going to be on chapter 1, 2, 3. Okay. If we had enough time, we are going to move to chapter 5. Chapter 1, 2, 3, and chapter 5, right? If we had enough time, we will talk about orbital maneuvers and interplanetary trajectories and lunar trajectories as well. And that will be it. But this orbital mechanics part of this class by itself has to be a separate course. So for whatever reason, people who were designing this program decided to bring these 2 courses together, flight mechanics and orbital mechanics. So you get a little bit of both. So you have to keep in mind that if you go out in the industry and you needed to know orbital mechanics, this is just a starting point to the knowledge of orbital mechanics. Okay, so this is something that you have to keep in mind. Now, orbital mechanics in general is a continuation of your dynamics, right? You have passed dynamics, hopefully with honors, with good grades, and we are going to build up on your knowledge of dynamics. Eventually, at some point, we are going to simplify things So if you don't remember your dynamics, I'm going to mention everything you need. I'm going to remind you whatever you need. If you don't remember your dynamics, you should be fine. Who did you have your dynamics with? Okay. Okay. So we are going to start with the dynamics of point masses, which is just a reminder of your dynamics with an application in aerospace engineering specifically, and then we move on from then. So we will start from with the very basic things. Before starting, is there any questions about the orbital mechanics part of the class? Like a specific question that comes to your mind. Okay. So dynamics of point masses. Hopefully, we will finish this part in only one lecture. That is my goal. If not, it shouldn't take us more than 2 lectures to finish this part. The first thing you need to know when dealing with dynamics of point masses, when you're dealing with the dynamics of point masses, you need to know about vectors. So what are vectors? Or what do vectors have? Vectors, compared to scalars, have a magnitude and direction. Okay. Hopefully, by this point in your education, you have seen this millions of times. You don't have any problem understanding what vectors are. You can add vectors if you have 2 vectors, A and B. You can add them together. And the addition of these 2 vectors will be a vector C. We have a lot of rules when it comes to vectors. For example, A plus B is equals to B plus A. So we can replace their situation. We actually define unit vectors. In this class, we are going to show unit vectors with U of A. Unit vectors of a vector A is your vector A divided by its magnitude. Something to keep in mind when reading the book, when studying the textbook. In textbook, vectors are shown with bold letters. I don't know how to do a bold letter here. So vector A is shown with a bold letter instead of this sign. I guess they wanted to make it easier on themselves, right? And magnitudes are showing with a regular non-bold letter. Not the absolute value or the magnitude value. The correct sign here is the magnitude value. So, but I'm just using the absolute value. So something to keep in mind by reading the text, not to be confused. Okay, so in this class, we are mostly concerned with the Cartesian coordinate system. Any vector in Cartesian coordinate system can have 3 different components in 3 different directions. So a vector A has the x component in the I direction, a y component in the j direction, and the z component in the k direction. The same is true for the unit vector, which is going to be equal to the cosine of theta x. That's the angle vector A makes with the x axis, right? I cosine of theta yj and cosine of theta z k. Then we have the dot product of the 2 vectors. When it comes to vectors, multiplications is we have 2 different multiplications, dot products and cross product. Versus in scalars, you only have just 1 simple multiplication. Just multiply them by each other. A dot product will definitely give you a scalar. A dot product of the 2 vectors will give you a scalar. Its value is equals to magnitude of A, magnitude of B, cosine of the angle in between. Right? A cross product will give you a vector, on the other hand. Its magnitude I'm going to use just a fluid is the magnitude of A, magnitude of B, sine of the angle in between. And again, it's in the direction normal to the two vectors, that vector. So if you have vector A, vector B, A plus B will be in this direction. A cross B will be in this direction. So the inner product, the outer product, that's also different names for these. How do we calculate the vector for the cross product? You have to take the determinant of this matrix in Cartesian coordinate system, of course. AX, AY, AZ, BX, BY, BZ. Okay. And a cross product of B cross A is equals to negative A cross B. Is there any question so far? The direction of this unit vector can be proven to be, or the unit vector itself can be found by doing the cross product and then finding the magnitude. Okay, so if you were told to find the direction of the cross product of two vectors, that will be the unit vector for it. Okay. We also have something called the back cab rule. So when it comes to cross product, A cross B cross C is actually equal to B dot A dot C minus C dot A dot B. So back cap. Okay. So let me ask you this one question. Is the solution to this calculation a vector or a scalar? To this, like triple cross, double cross product. Is the solution to this a okay? It is a scalar. So we have one scalar, and Nila just came in, so I'm not going to ask your opinion. Just let you catch up.
Oh, no, the dot product. Okay, yeah, scalar.
A scalar? Okay, we have two scalars. And we don't have anything from the online people. Which is?
Those B and C are cross products on two vectors, and those turn scalar times, so another vector would be a vector.
This one. So you're looking at this part of it, right? The right hand side. Which part were you analyzing? So you're saying this will be a vector.
I'm saying that would be a scalar, and then times the vector outside would turn into a vector.
Okay. Your final conclusion is correct, but the way you got there is wrong. So this is definitely a vector, right? The cross product. The dot product will give you a scalar. Let's look at here. We have a scalar here, we have a scalar here. Just a number. A number multiplied by a vector is a vector. Yeah. A number multiplied by a vector, that's a number, it's not a vector anymore. Multiplied by a vector is a vector. So subtraction of two vectors is still a vector. So, okay. So, and hopefully we are all familiar, we are all already familiar with these operations, and we don't need to solve any examples on them. That's why I'm just going to move on to the next part of the chapter, which is the kinematics. just a small review of kinematics. So we did the vectors. Let's do kinematics. The first thing you want to define when dealing with kinematics is a position vector. So we have a frame of reference on FOR, and a point P, dynamics of point masses, so we're always dealing with points. A point P is moving on this line. Your position vector is going to be equal to x of I, x of t, y of t, j, plus z of t, k. Okay? You forgot your mask. Yeah. So please put on your mask. Okay. So we have the position vector. And the velocity vector, we can define the velocity vector as dx dti plus dy dtj plus dz dtk. We can say the same thing for the acceleration vector. It's also a function of temperature, also a vector, dvy dtj dvz dtk. Okay. And something to keep in mind is that the derivatives of the time derivatives we usually show with r dot, the dot on the top of it. So A is going to be equal to v dot equals to r double dot. Time derivative. This signifies the derivative with respect to time. And the path this particle P is moving on is called the trajectory. So we can define the trajectory as the locus of the points that this particle occupies when it moves from when it moves through a space. So by this type of definition of trajectory, we can safely conclude that your velocity is always going to be tangent to your trajectory. So velocity vector is going to be equal to a velocity magnitude, u of t. And u of t is going to be tangent, the unit vector tangent to your trajectory. Okay, is there any questions so far? We can also find the space traveled, which means that how much it has moved on this trajectory, ds, with the magnitude of velocity dt. Okay? Which essentially means that your magnitude of velocity is going to be equal to ds dt or s dot. So this is something that you always have to be mindful of. Magnitude of velocity is going to be s dot. The velocity vector is going to be r dot, right? And s is the distance traveled on this trajectory. R is the vector from the center of the frame of reference, or the center of the coordinate system. Okay? Unit vector, the tangent unit vector, of course, we can find from this formula is going to be your velocity vector divided by the magnitude of velocity, which means that it's going to be Vx, Vi, Vy, Vj, and Vz, Vk. Acceleration, on the other hand, can have two components. One, tangent to your trajectory. One, normal to the trajectory in the u of n direction, un direction. So we're going to get a tangent ut, a normal un. I'm hoping you recall from your dynamics that a tangent is equals to v dot is equals to s double dot. Again, here we are talking about the magnitude of a tangential acceleration, which is going to be calculated with s double dot. Trajectory, the amount of change in trajectory with respect to time, right? The space you have traveled with respect to time. But the vector, the acceleration vector, is r double dot. This is something that you need to make sure that you are clear on. And the normal acceleration is v squared divided by rho, or r. In dynamics, we usually call that rho. Rho is the magnitude of actually, it is the curvature, wherever that is. The radius of the curvature at that specific point, right? So if you draw a circle using this point, rho will be the radius of that. Okay. Is there any questions?
What's the origin represent?
That's the origin of frame of reference. Yeah. That's just you're talking about this, right?
Mm-hmm.
That's your frame. You can put your frame we are going to talk about this as well. But you can put your frame of reference anywhere, right? That's from your dynamics. So that's the origin of your frame of reference. In theory, we have an absolute frame of reference, which is the inertial frame of reference, right? Which what we call inertia. But that's just in theory, right? We will talk about it a little, just in this lecture, a little more. So, okay. So we have two unit vectors. Let me clear here a little bit. When it comes to this point P, the movement of point P in this trajectory, we have two unit vectors. Let's say this is P, tangential u of t, and u of n. We can define a third one, u of v, which is called the binormal unit vector. Let me write it here. This binormal is essentially tangential unit vector cross product of the normal unit vector. Okay. We can also show that this can be calculated using the velocity and acceleration vector, the cross product of those, and the magnitude of this cross product divided by the magnitude. So this is a direction of the cross product of velocity and the acceleration. As this particle P moves on this trajectory, it sweeps an area, right? Let me actually make it a little bigger. It sweeps this area when it comes to the origin. There is angle phi. That is called the sweep angle. And the sweep angle is equals to, we can be calculated using ds. So your d phi is actually ds divided by your curvature. We can also relate the changes in the sweep angle to the changes in position vector. Any questions so far? So this is the extent of things you need from your kinematics. As long as you understand the tangential and normal acceleration, as long as you understand the centrifugal force, you should be fine. Okay. And again, this lecture, we are only focusing on the basics and whatever you need from the previous classes, your basic physics, your dynamics, and so on and so forth. Okay. So next part, we need to talk a little bit about Newton's law of gravitation. Who is familiar with this law? Exactly. So the gravitational force is equals to G. That's the universal gravitational constant. Gravitational force between two masses of m1 and m2. And distance r is equals to the masses of the two divided by the distance squared multiplied by the universal gravitational constant. Okay. And this universal gravitational constant is 6.6742 10 to the negative 11. I always forget the units myself. Meters cubed, kilograms second squared. Okay. If one of the masses is much bigger than the other mass, you are essentially calculating the weight force. We are going to call this force the weight force. And we are going to show the larger mass with capital M. Smaller mass. And the distance between the center of the two is going to be equal to 1. Let's rearrange this. Your W is equals to M gm divided by r squared. And this is what we call G, or the gravitational acceleration on Earth. So G multiplied by the mass of the Earth divided by r squared. It is very obvious from this equation that your gravitational acceleration is going to become smaller and smaller as you move further away from the surface of the Earth. But on the surface of the Earth, the gravitational acceleration, we are going to call it G naught. And this G naught is G m divided by the Earth's radius squared. Okay? And we can find G at any elevation as a function of G naught. G naught divided 1 plus Z divided by RE squared. And Z here is your altitude from the surface of the Earth. So the distance from the surface of the Earth, not from the center of the Earth. Is there any question so far? Which one? This one? That's correct, yeah. Z is the altitude, is the distance from the surface of the Earth. So if you're flying at 10,000 meters, that's your Z, yes.
So with the, I guess, rocky terrain, the surface of the Earth fluctuates, is this going to fluctuate as well? But I guess the perturbation of Earth?
Okay, that's a very good question. So, yes, but it's a little more complicated than that. So in most of our analysis, we are going to assume that Earth is a perfect sphere, or any planet is a perfect sphere, right? So we are not thinking of a rocky terrain, not just a rocky terrain. We are not thinking about Mount Everest as well. So yeah, that's something that you have to. And in orbital mechanics, when you are at a very high altitude, it really doesn't matter as well. It doesn't matter that we are going to see. We are going to do a rough calculation. We're going to see like the difference is 0.1% if you bring in all of those complexities. So yeah, it is definitely different at different parts of the Earth, because the altitude is going to change, the Earth's radius is going to change, and also Earth is not a perfect sphere, right? And we have like different materials. It's not just a homogeneous material as well. So a lot of complexities come into play when you're dealing with this.
The heaviest part of Earth is core, and that's magma. Does that, like, mass fluctuation matter as well?
Definitely, yeah. But that's how much does it matter is the question you want to ask, as an engineer, and not as a physicist, I guess. Okay, so let's see. Let's solve this example problem, and this is, let's call it an attendance quiz. I'm not giving this attendance quiz because a lot of people didn't attend the class, but they are online. So I had this in mind from before coming to class. So this is a book example. Okay. So it's a very interesting example. The text of the problem makes it a little complicated, but whatever you have here is essentially something you could calculate after you pass your physics 2, right? So the knowledge in this problem is not very specific, the knowledge you need. So we want to show that in the absence of an atmosphere, the shape of a low altitude ballistic trajectory is a parabola. Okay? I'm going to assume the acceleration of gravity, g, is constant, and we want to neglect the Earth curvature. So you have x, y, x naught and y naught as the origin. You have a low altitude ballistic trajectory, which means that you are going to shoot it at a velocity v, which makes that angle, your book calls it a gamma naught, but whatever you want to call it. You want to show that this trajectory is a parabolic trajectory, or is a parabola. Which essentially we have to find the equation of y as a function of x. This is what we are looking for. We want to find the trajectory, right? So how should we approach this problem? I'm going to give you a couple of minutes to work on this, but we essentially are going to work on this together. The first thing you really need to answer here is what kind of motion you have here.
V naught cosine thetas, and that equals x, and v sine theta equals y.
That's the two components of velocity. That's correct. But what kind of a motion is this? What is the only acceleration available here? Gravity. So what does it mean? Free fall, right? So acceleration, x double dot is 0, y double dot is negative g, right? That's the acceleration you are going to have. Based on this, what is the equation of motion? Or let me put this way, how would you find the location at each point? How would you find the x direction location at each point? That's a non-accelerating motion in x direction, right? You can also take the integral twice. Go ahead. X equals to what? Vxt plus x naught, right? What is Vx? V naught cosine of gamma naught. So V naught cosine of gamma naught. What about y?
Vy minus g. Or you say Vy minus 1.
No, because this one is an accelerated motion, right? We took the integral here twice, and we got to this. What will happen to this when you take the integral twice? So let's take the integral. So y dot is going to be negative j, negative g, sorry. Negative g what? Negative g y, right? Plus y naught, plus a v naught, or y dot naught. Let's call it v naught y, right? Which means that y is going to negative 1/2 gt squared. This is t. T squared v naught y t plus a y naught, right? Yeah, you remember this free fall equation? Right? This is one of the oldest equation you have seen when it comes to kinematic analysis. Okay. So we have these two equations of motion. And v naught here, v naught y here, is v naught sine of gamma naught. I'm going to rewrite this equation for t to substitute in the other equation. So t is going to be equal to x minus x naught divided by cosine of gamma naught. So plug that in here. I'm going to continue on top. Plug that in here. You're going to get y is equal to 1/2 g x minus x naught divided by cosine of gamma naught squared, right? Plus v naught sine of gamma naught x minus x naught divided by cosine of gamma naught plus a y naught. So this is a parabolic function, right? Everything is constant. There's constant values. We don't know what are the values, but these are just constant parameters, except for x and y, right? Okay. So let's talk about, so we talked about gravity. Let's talk about Newton's laws of motion as the next step. Again, this is also a reminder. Let me actually delete these, like these. off the board.
So this was for elliptical orbit. Is it the same for concentric? Like circular?
What?
This was for an elliptical orbit, right? The parabolic.
We assume the Earth curvature, the Earth is flat. This is for a flat Earth.
So was this just a free fall?
That's what it said. That's what, yeah, exactly. Very simple. Okay, Newton's law of motion, laws of motion. What are the three fundamental laws of motion? First, what is the first law? Inertia, right? So if something is moving or if something is not moving, it is going to keep moving or not moving if there is no force applied to it. Second one, the total of the forces is equal to mass multiplied by acceleration. And the third one, if an object exerts a force F on another object, the other object exerts the same force onto the original object in the opposite direction. So we also defined an impulse. Have you seen impulse in your dynamics? That's Ft or F delta T. Integral of F net. That's something you are going to see in propulsion as well, right? Which essentially means that your Ft, your impulse, is the changes in momentum between two different directions. V2, V1. Between two different times. Total momentum, total moment around the origin, m dot mo net is your r multiplied by the cross product of the net force. Which is equals to r cross product of A. Which essentially is, let's replace that with dv dt. And then I'm going to continue here. Okay, what can you say about this term here? d dt of r cross m v. What is this term? No, just expand this for me. Okay. Plus right? Is this correct? Yes. So that's d dt of A multiplied by B. That's it, essentially. Okay. This is the same as what we already have here. So if we move this term to the left-hand side, we can substitute this whole thing for r multiplied by m dv dt. So d dt of r and v minus dr dt, which is essentially velocity vector and v. We're assuming m is constant, so we can move it around. And I mean, if it wasn't constant, it is not a vector. We can move it around, and the cross product of a vector by itself is always 0. So this part will go away. So your total momentum is going to be equal to total moment. Net moment is equal to ddt of r plus r, that's not plus, r cross mv. This is called angular momentum, or h naught. So your net moment is the time derivative or changes of angular momentum in time. You can actually take the integral. Your angular momentum is going to be the integral of t1 to t2 m dt. Okay, so this is called, that's h, I'm sorry, that's, okay, this is called, or delta h, we can actually read. This is called, this integral is called the angular impulse. So we defined a linear impulse, and we also found an angular impulse. So this is essentially the same, and it's analogous to the linear impulse equation. Linear impulse is equal to the changes in linear momentum. Angular impulse is equal to changes in angular momentum. Okay, is there any questions? Have you seen this before, the angular momentum in your dynamics? Hopefully. Yes. Okay, that's good.
What's the one in between the moment and the net?
That's a parenthesis. That's a, yeah, for whatever it is, your book uses this. I'm following it. Okay, so the next topic that we need to talk about is the time derivative of a moving vector. So the idea is you have a frame of reference, x, y, z, and you have a vector that is moving. Time t here, time t1 here, time t2 here. The only condition we have for this vector is that its magnitude does not change. So its direction is the only thing that is moving. So that changes in magnitude over time is 0. This, we can actually show that the time derivative of dA dt, the vector itself with respect to t, is the angular velocity of this vector cross product by the vector itself. And the proof of this is in the book. And if you just give me the proof, you will get a bonus point for it. So submit this by Thursday, you will get a bonus point. This concept is actually going to be very useful to us. I'm hoping you have seen all of these before. That's why I'm not like focusing on them so much. But if you haven't, that's very. It's just the equation that you have to know. This is a concept that we are going to use a lot in the next 20 minutes, and also for the rest of the class, it is going to become handy in time derivative. Let's talk about different frames of references. We have something called an inertial frame of reference. X, or we usually use capital Y, capital X, and capital Z for it. The inertial frame of reference doesn't move, doesn't rotate, doesn't do anything. It's just an absolute frame of reference without any movement. And eventually, at the end of the day, it is going to be our original, whatever we are calculating our things based on. We also can have a moving frame of reference, X, Y, Z, which can rotate, it can translate, it can move, and can have a lot of different properties. And what we want to do is we want to find the position of this vector B with respect to the moving frame of reference as well as the absolute frame of your inertial frame of reference. Give me a minute. I'm getting the mass fatigue. I run short of, I run out of breath constantly. I'm just getting old, huh? No, I don't want to get into problem with the university, and I'm already vaccinated, so we don't. But they take your picture, so, and they send the picture to. They take your picture, they send it to your email. If you're a faculty, they send it to the department chair that this guy is not wearing a mask. So, yeah. I guess. Okay, so, yeah. We want to find a vector for different frames of reference. Let's do the absolute frame of reference first. So vector B is going to be equal to B of X I plus B of Y J and B of Z K. I keep forgetting about this, and I want to bring this up with you all. When I sent you the email with the voting, most of you didn't understand what I meant by ranked choice voting. Like I got it. You didn't? So essentially, when I ask you to do a ranked choice, so you don't follow politics at all then. When I say ranked choice voting, what I mean is that you give me the choices based on your priorities. So if your priority was the option 1, your first, you have to give me your second, third, and fourth priority. And all of them will be counted. So your second priority will get half a vote. Third priority, 25% of the vote. Fourth priority, 0 vote, right? Yeah, a lot of you, I mean, did I say it has to be, in the email I didn't say it has to be unanimous.
You did say, it said almost unanimous.
Almost unanimous. I mean, eventually, yeah, when I tallied the votes, it was almost unanimous. You're correct. But if you had more people in the class, I would assume. But it was interesting to me to see that you didn't understand my point. I guess I did. They're online.
They'll be here in the next class.
Yeah. Yeah, hopefully. Okay, so let's continue. So your dB dt for this version of your vector B with respect to your inertial frame of reference is going to be the regular dBx dt I dby dt j dBz dt k. Okay? And this is capital I, capital J, capital K. Well, if you write this vector for this moving frame of reference, let's say you have everything is in small letters, so Byj plus Bz is the derivative with respect to time, is it going to be different? Or is it going to be the same as this one? What changes? No, let's say this is time t1, this is time t2. The only thing that has changed here is your frame of reference. Yeah, exactly. The solution, what I'm asking you about is the equation. Is the equation going to look different? I mean, the solution, yeah, that's definitely different. That's for sure. But do we have to, for the time derivative, is it going to be dBx dt I plus dBy dt j plus dBz dt k? Exactly. Exactly. Thank you. So since the frame of reference is changing, your I, J, and K are not constant anymore. They are going to rotate and move with actual. So your I, J, and K are definitely going to change. And since these are unit vectors, their magnitude does not change at all, right? So their changes with respect to time can be formulated like this. So changes of this B with respect to time for this frame of reference, when you write the B for this frame of reference, is going to be dBx dt. So dB dt is going to be dBx dti. And when you're taking the derivative of this whole thing, this is taking the derivative of a multiplication. So it should be dBx dt multiplied by I, bx multiplied by di dt. Is this clear? Okay. dby dt j, dBz dt dt k plus bx di dt plus by dj dt plus bz dk dt. Okay, and then we can. I'm going to continue on the next part of the board. So we have all these derivatives: dbx dt, dby dt. I'm going to not write them. So we are going to do bx di dt omega multiplied by I plus by omega multiplied by j plus bz omega multiplied by k. And omega here, since we are dealing with a frame of reference, for the angular velocity, we are going to use capital omega. And it's a vector. So that's the angular velocity of a frame of reference. Okay. Is there any questions about this? No? So the first part, this part, when it comes to moving frame of reference, we are going to call dB dt, or the relative time derivative. So your total dB dt is going to be equal to a relative time derivative, which essentially means that we are taking the derivative of b relative to the frame of reference, assuming that the moving frame of reference doesn't change, doesn't move, right? And then for the movement of the frame of reference, you are going to have, you can combine this with a omega cross product of b. You can actually bring all of these together to omega cross product of b. Okay. So for a bonus point, I want you to find the second derivative of b using the same method. Just plug the values in and find the second derivative. And the second derivative, I'm going to write it here just so you have it, is going to be ddt of dB dt, or the second, or the relative second derivative, plus d omega dt cross b plus omega dB dt. Just make sure. Okay, yes. So the relative part of dB dt, but then eventually you can expand on this as well. This dB dt is actually this value. So relative dB dt plus omega cross b, right? So it is going to give you a very huge equation. We actually have the I'm going to ask you eventually in a homework problem, but it's a book example as well. So you can just find the solution from the book. I'm going to ask you to find the third derivative. But there are a couple of points that you need to keep in mind, that this is also a time derivative of a moving vector, right? So you have to do this analysis for the dB dt relative. You have to essentially apply this equation, do it for the dB dt relative as well. You have to plug in the value of this here as well, and then simplify it a little bit. It's going to get a huge one. It's a little. You have to make sure that you are consistent. You focus. You have you keep focus throughout the process. But eventually, it is not going to give you a very simpler thing at the end. But yeah, I guess you have to have it. Okay, so. And we're going to see why this is useful in a minute. But before moving on to that usefulness of the time derivative, let's actually talk about the position vector. So when it comes to position vector, your position vector is the position vector of the frame of reference when it comes to compared to the inertial frame of reference, right? Plus a relative frame of reference. So the distance from that point B to the moving frame of reference, this finds the distance from the origin of the moving frame of reference to the inertial frame of reference, okay? And this part is going to be your x, I, y, j, and z car, right? This is your, for your velocity, you're going to have the velocity of the moving frame plus the derivative of your relative position vector, which essentially means that if you apply that analysis, your velocity is going to be v naught plus dr relative dt, the relative time derivative, which is your, which we are going to call relative velocity, plus omega multiplied by your relative position vector. Are we clear on this formulation? So your velocity is going to be equal to v naught plus v relative plus omega trans r relative. And this is just some mathematical operation. I'm pretty sure you should be able, if you were confused, you should be able to derive this on your own, because they look a little complicated maybe at the first glance, but it's just a lot of mathematics. For acceleration, we can do the same thing. Acceleration is going to be second derivative of your position vector with respect to time, which essentially is going to be this huge equation. Has to replace the second derivative of the position vector with respect to time. Okay, so let's apply all of these to something that is moving around the Earth, right? That's the eventual goal. Let's say this is your Earth. Again, the assumption here is that Earth is a perfect sphere. We are going to have an inertial frame of reference. Y, X, and Z. This does not move, does not rotate, and doesn't move at all. We can have another frame of reference, which is going to be a moving frame of reference. X prime, Y prime, and Z prime that is moving from around the Earth axis of rotation. So Z itself is going to lie on top of the inertial frame of reference we have had, and then we are going to have another frame of reference on the surface of the Earth. Let's say this is here, X, a small x, Y, and Z is going to be the altitude. So a point P, I ran out of colors. Oh, I'm yellow here. A point P here is going to be like this. So this distance is going to be Z. This distance is going to be Earth radius. Okay? The projection of this here is going to give you the north latitude, phi, and this here, the projection on this axis is going to give you the angle lambda, which is called the east longitude. This angle is actually called theta g, as related to the rotation of the Earth. Okay, that XYZ over there is called the topocentric horizon coordinate system, the green bar. That's on the surface of the Earth. Topocentric horizon coordinate system. So I guess that's it for the definitions. X prime is also on the Greenwich meridian. It's moving with that. And Y prime is perpendicular to that. Okay. Is there any question about this? We have 3 different frame orders. That's the only thing you really need to know. All of the other ones are the definitions. So for this, we want to calculate the acceleration and the position and the velocity of point P that is at a height z from the surface of the Earth. Okay? The position vector R, the relative R, is going to be equal to RE plus ZK. Okay? So we are writing the position vector and velocity for this x prime, y prime, z prime. Okay? You're moving from a reference. It is on in the k direction. We are writing it for the green one. So your v relative is going to be equal to d relative with respect to t, which is going to be equals to d dt of RE plus Z K. So what is this? How can we calculate this? That's going to be d dt of, or let's call it this way, K d dt of RE plus Z plus RE plus Z dk dt, right? What is this derivative? The radius of the Earth we assume to be constant. So Z dot K. And what about this part? dk dt. What is dk dt? Look at over there. That's a derivative of a moving vector with respect to time. What is that? dk. That's a moving vector, right? The moving vector here is k. It's the same thing. The magnitude doesn't change. It's just rotating, right? Or moving. So you're going to get RE plus Z omega cross K. Okay, so the next question is, what is omega of the Earth? That's actually where these angles come into play. Omega of the Earth can be calculated using the equation I'm going to write on the board. Omega of the Earth is equals to negative phi dot I, angle phi here, right? Plus lambda dot cosine of phi j plus lambda dot sine of phi k. Okay, so we have the omega. How can we calculate omega cross? Oh, it is already 1120. Omega cross k. How can we calculate this value? Let's just do this, and then we don't have that much left of this chapter. So I guess let's just do this, and then we'll pick up on Thursday. No, so dk dt is omega dot k, but we have the omega. So what would be the solution to this cross product? What is k cross k? 0. So this part, 0, right? What is k cross I? Or I cross k? What is I cross k? Negative phi dot j, right? And then you're going to get, for this one, you're going to get cosine of phi k, right? That's the idea. I cross k is j, and so on and so forth. K cross k is 0.
Now you said J cross K is K.
That's I. I'm sorry. You're right. I'm sorry.
What is that sign in front of the cosine? Looks like an upside down B.
Lambda. That's capital lambda. So we have a small lambda like this, capital lambda like this. Again, lambda. This is how much you have rotated from the Greenwich meridian on your, that signifies that value. Okay, so let's stop here. We are going to pick this back up on Thursday. We will finish chapter 1 on Thursday, whatever we need from chapter, but there is a numerical integration part to chapter 1, like the Runge-Kudal method and all of the MATLAB analysis. We are not going to do that because I know you are doing a lot of MATLAB programming in your vibration, so you're already becoming familiar, and you have already passed the numerical method, so you know the Runge-Kudal or Runge-Kudal, as some people call it. At least you have heard about that method, right? So we don't want to redo whatever you have done before or whatever you are going to do anyways. So let's stop here. And we are going to see each other on Thursday, hopefully. And by Thursday, I'm hoping to have graded all of your exams and homeworks by this point, so you have a good idea of where your grade stands at this point of the class. I assume since I gave you a take-home exam, everyone should get an A from the exam, hopefully.
Have you been posting the grade on Blackboard?
I have not. Okay, so we had one question from Lawson. I don't know when he asked this question, but I'm sorry, Lawson. I didn't see your question. Okay, so I'm sorry, what were you asking?